Okay. Oh,
Is Chris' camera working? All right. Okay, good. Right. Maybe turn this off.
All right, are we ready to start?
Yes.
All right, well, welcome everybody, attendees who are funneling in. This is the Uncovering the Hidden Sun panel discussion that we're hosting here at the National Society of Black Physicists. Particularly the Astro group wanted to put on something for this upcoming Total Solar Eclipse. So we have some experts here who are going to talk about the science that we can learn from eclipse and what the total eclipse is. And we're hoping to have opportunities for you folks in the audience to engage and ask our panelists about this. If people miss it or you find this important, you want to share it, this recording will be posted on the NSBP YouTube channel. So feel free to share it. And I'm going to hand it over to Dr. Samaiyah Farid.
Morning, everyone, or afternoon, depending on your time zone. My name is Dr. Samaiyah Farid. I'm a project scientist at the National Center for Atmospheric Research, which is in Boulder, Colorado, and I study the solar corona, the outer atmosphere of the sun. Today, I'm primarily going to be allowing Dr. Alphonses Sterling to talk. He is a scientist at the NASA Center at the Marshall Space Flight Center in Huntsville, Alabama, and he is a solar expert, solar eclipse, and solar science expert. And he will be giving the primary presentation today, and then I'm going to come in at the end to talk about some ways that you all can be involved in citizen science projects and public projects. So with that, I'll let Alphonse take it away. You can share your screen and begin your presentation. If you have questions throughout the presentation, you can use the ask question function, or you can, and one of the hosts will direct your questions at the end of his presentation. Thanks.
Okay, thank you, Dr. Farid. Let's see. Okay. Now I want to pick one of these. Let's try this one and see what happens. Hold on. Okay, are you seeing that?
Yes, we can see it.
Okay, all right. So I guess it's kind of under control here. Okay, well, hello, everyone. I'm happy to speak with you today. And my name is Alphonses Sterling, and as Dr. Farid was saying, I'm a solar physicist. I'm actually employed as an astrophysicist at Marshall's Space Flight Center in Huntsville, Alabama. But my specialty is really the sun, so I study the sun and various things that go on with the sun. So I can give you some idea about that, I hope, with my presentation. Okay, that started. So let's get going. So I'm sure we have a variety of good folks who will be looking at this, or maybe the recording later. And so just to make sure we're all on a equal footing here, I want to talk a little bit about what eclipses are, which most of you are no doubt familiar with. But basically, I define it as when one celestial body falls into the shadow of another. And then one or both, depending on your vantage point, you're seeing an object being obscured by a celestial body, or you're being obscured. So to make it on more concrete terms, we'll talk about solar eclipses, since that's what this is. And in this case, the moon comes between the sun and the earth. And it does so in such a manner that the shadow of the moon falls onto the earth. So just like on Earth, you have a bright light and you stand in front of it, then behind you is the shadow. And so it's the same with the body in space. So the moon casts a shadow back behind it. And it's really interesting because it turns out that shadow just barely touches the earth. And in fact, it's so close to exactly falling onto it that whether it does actually, the full shadow, whether the full shadow of the moon actually reaches the earth depends on where in the orbit the moon is around the earth. So the orbit is not perfectly circular, it's elliptical. So if the moon is at its far end of its orbit, then the shadow actually doesn't quite touch the sun. And so in that case, the moon does not totally cover the sun, but if you're in the right location, you can see the moon cover the central portion of the sun with a bright rim around the outside. That's called an annular eclipse. And actually, there was an annular eclipse last year, 2023, October 14th. And it actually was visible as an annular eclipse in some of the places that it will be seen as total this year. So anyway, that is what an eclipse is, or a solar eclipse. And this time, this shadow of the moon will touch the earth in such a manner that the moon is completely covering the sun. But as I said, that path is narrow and it sweeps across the surface of the earth as the bodies are in motion. The moon is in motion around the earth, and the earth is also spinning below it. And that combined effect means that shadow sweeps across the earth. And this is the way that path goes for this eclipse. So you'd see it starts out here in the Pacific someplace, and then it goes over Mexico, and then a huge swath of it goes over the United States. And that's why it's going to be very exciting for those of you who are in this path of totality in particular. And if you're outside of it, then you're going to see the sun partially covered by the moon to varying degrees, depending on where you are at relative to this path. This map is on the NASA Eclipse webpage. You can Google it probably more easily than I could, but you do NASA Eclipse 2024 eclipse path or something like that, and you'll get this information. So here it is. Now, this is something this map is of interest to people like me, and well, in various ways. It's of interest to people like me from a scientific standpoint, those of us who want to study eclipses for a science purpose. But it's also of interest to a different type of people like me, ones who just really think eclipses are cool as anything, and we want to see them when we can. And so what this is the colors are showing the average cloud cover of various parts of the eclipse path. And what people do is they look on the date of the eclipse. So April 8th, you look at April 8th, back for as many years in the past as you can. And you look at these locations along this path, and you look at what the cloud cover was like at about the time of the eclipse on that date. And since we can't tell the future, we look in the past and see what it is. So when you do that, you can make a probability of how clear it will be at that location. And the redder it gets, the more ominous it gets. It means more cloud cover. So let's see here. Over here, we're getting to like 80% and 90% cloud cover at this time, and here it's quite good relatively. It's like 50%, so it's still not great. Mexico is quite good. It's about 20 and 10% of the time only was cloudy. So these are the places where there's the best chance based on these historical records of seeing the eclipse. So if you live over here in Northeast Maine, does this mean that you have to give up on seeing the eclipse? No, it doesn't. Because as I said, this is an average over many, many years. When it gets close to the eclipse for this day, for this year, the weather is going to depend, what the storm systems are for that particular period of time coming through and all of that. And it could well be that it's totally clear up here in Maine and northern New Hampshire, and it could be socked out here in Dallas and in Austin, and even in Mexico, so it's a probability. So as it gets closer, that will become more apparent what it's going to be like. But it's still, it's intriguing if it's cloudy too. It can be disappointing, well, it's disappointing you want to see it, but it's still an incredible experience and other things you can actually enjoy too, even if that is the case. Okay, so that is this eclipse. So now you see this path that I've drawn here. Well, because the motions of the planets and other celestial bodies like the moon and the sun are extremely regular, just basically following Newton's laws. They knew about Newton's laws before Newton did, and Kepler's laws too. We can say with a high degree, an incredibly high degree of accuracy, where eclipses in the future will be, especially over the next 100 or few hundred years. And this map here, this is partially covering, the zoom is partially covering my screen, but I think it goes up to 2030. And it shows the eclipse paths for the current one, the 2024 one is right here. And then I mentioned there was the blue are the total eclipses, and the red are the annular eclipses. So I mentioned in 2023, there was an annular eclipse, that is this one. And it intersected here in Texas. But these are the paths, so these narrow paths. And so you can see where they will be in the future. So 2027, it's actually, this is quite a nice long one in Northern Africa. And Australia is going to have some more 2030 here. Now, one thing will stand out to you. After these two, there are no more here in the United States. This one here was in 2021, and it was in Canada. It looks like Ontario and Quebec provinces of Canada, so it's not even the US. So until 2030, at least, you aren't going to see any more in the US. And in fact, it's not until 2044, 20 years from now, when there's going to be another one where these lines just happen to intersect in the United States. And then it's like Montana and the Dakotas. So in short, if you don't want to move too far and you're in the US and you plan on being here for a while and you want to see one, then you would be advised to try to see this one. And this is why we speak of eclipses being rare. They're narrow paths, and they don't repeat over the same location very frequently at all. I mean, they do, but it doesn't happen that much. Also, the duration of totality when the moon completely covers the sun is very short. In this time, it will be 4 minutes or something, depending on where you're at in this path and so forth. And that is actually relatively long. And the longest possible, in fact, is only like 7 minutes and some seconds. So that's the longest possible. So they can be very short, lasting only a few seconds. So anyway, a lot of things conspire to say that these are very rare occurrences. And I haven't even gotten into the weather bit, where that can disrupt things. And if you're trying to observe, I haven't gotten into the bit where the equipment also knows that an eclipse is coming, and it knows the time, and it knows that it wants to cause havoc by not working, by lens caps falling, and all sorts of chaos can happen around eclipse time. Okay, so I've talked about that. Eclipses are exciting, but most of the audiences here, I think, are aware of this, but I certainly have to say it. You can never look at the sun directly with your unprotected eyes. I should say the uncovered sun. So during a total eclipse, it's only those few minutes when the bright part of the sun is totally covered by the moon, that you can look at the at the outer edges of the sun is what you would see. But when that bright part is there, and if you're there watching it and that bright part comes out, look away. It's not safe. And the New York Times just had an article a few days ago about some folks from the 2017 eclipse. Many of you will be aware of that. We had the one in 2017, August 21st in the US. And it was seen elsewhere too, of course. But it had an article and it talked about some folks who stared at the sun for a number of seconds, and they had eye damage, sometimes permanent. So you don't want to do that. You want to protect yourself. That's number one. Okay, so what are some of the things you can do? So there are eclipse glasses, if you're around some event where there's a NASA event, they will have official ones that you can use. There's an official ISO number that goes with these, and I didn't even quote it here. It's easy to find, like on the NASA site, but I didn't bother to even quote that number here just because even with that, you have to be cautious because back in 2017, that kind of worked because the official ISO number came out and the glasses that were official had that on there, and the people make fake glasses. It's incredible, but they do, and then they sell them. Back in 17, they weren't really caught up with this ISO number. And so, the glasses that had the ISO number were pretty much guaranteed to be safe. Now, unfortunately, these other scoundrels are aware of this, and sometimes they may put that on there. So if you get these glasses, you want to make sure that they're totally dark. Like if you're looking in just your room with them, you shouldn't see anything. Unless you're looking at a very, bright light, then you should see like the, if it's what we call the incandescent light, you can see just the very brightest part of it, and you want to inspect them to be sure that they don't have breaks in them and so forth. Another thing you can do is welding glass. So welders, maybe some of you weld, I don't, but I would go into a welding shop at sometimes over the past, and I would go in and I would ask for shade 14 welding glass, and the guy would say right away, "Oh, there must be an eclipse coming," because for welders, you're welding with this very bright arc, and apparently you use different shades depending on how bright that arc will be. Well, it's very rare apparently when you would ask for one that is as dark as shade 14, but this is what you would use for eclipses. And these are good. They protect against the infrared and ultraviolet light, which is really what damages the eyes as much as the bright light you can see. So that is an option. Another method, and this is actually the safest, is to not look at the sun. You don't look at it directly. You look the other way. And an idea is use a pinhole camera. So this can be as simple as having 2 pieces of cardboard or just heavy paper. You poke a little round hole in one of them, and then you hold it in front of the other, and you put the second one down away from the sun. So the one with the hole is facing the sun, and then the one that doesn't have the hole is put into the shadow of that other one. And you'll see a projection of that hole there. And during the eclipse, during the partial phases, you'll see chunks of that hole taken away, which is a partial eclipse. And you can do this with colander. You can see lots of little eclipses. Even trees and leaves can show the same sort of effect. So there are lots of ways around that. And even when I have these glasses or this shade 14, I really only use that to glance at the sun. I just have to know it's really there and it's really being eaten away, and I'm good. I don't really see the need to just stare at it. And then the truth is, even using these glasses and things, I find it a little uncomfortable to just stare at it. So I don't, and I don't see a point to it because it's a slow progress to cover up. But every few minutes you can just glance at it and say, "Oh yeah, and oh, it's a lot more, and it's more." Okay, and certainly I'd say it's really tricky to. I would not use. I would just say to avoid using binoculars or telescope without if they don't have the proper filters on it. Yeah, just and those aren't, you can't use your glasses, that material, and just put that over the binoculars or something. You need the filter made for it. These solar filters, special filters. Okay, so what to expect? Okay, this was actually from the Annular in Texas, and so during the partial phases, then if you're outside the path of totality, this is what you'll see: varying degrees of the moon eating into the sun, and more and more it gets more and more exciting. And this is starting to get really exciting, and you can actually see changes around you too. You can, from like around this time, you can actually start to notice it's getting noticeably darker, outside, and other strange things happen too. For example, the shadows that you cast on the ground. Now, your shadows are used to the full sun, right? That's what you see. And because of that, the edge of your shadow is actually kind of blurry. You don't notice it because, it's every day. But it comes from this whole solar disk. And so it's not a sharp edge when you have the shadow. When you progress in the eclipse, it's coming from a very narrow part of the sun, and the shadows just get strange. Their edges get sharp, and it's kind of it's an eerie glow around it. It's fascinating scenery. And then it gets really close. And then all sorts of things happen. And then totality starts, and then you see what you're unable to see at other times. Now, this is when the moon is totally covering the bright part of the sun, and only the outer atmosphere of the sun, called the corona, which Dr. Farid was saying that she studies, and we study it too. For centuries, this was really the only way people could see the outer atmosphere of the sun. And so it was hard to learn about it because you only had 2 or 3 or 4 minutes, and when you hope it's not cloudy, to be able to see this, to get your measurements in, hope everything works, and to get your data. So it's something. So if you're looking at the eclipse, then you will see this. You will also, with this phase of the solar cycle, especially, we can expect to see several of these things. These are called prominences. Forgotten, I may talk a little bit more about these, depending on how time goes. But anyway, these hang off the edge of the sun, and they have a very distinct red color too. So those can be seen around the limb, and there's a closer view of it. And the corona, now actually it's rather hard to photograph the corona of the sun. And for those of you thinking of trying to do it, if this is your first eclipse, I would suggest that you do not try it. Now, if you have your, your phone camera and, you want to take a few shots while you're there, that's fine. But I guess what I'm saying is, if you're going out to make it really your project, then I'd say wait for your second or third eclipse to really, make an effort for it. I will say that I saw 3 eclipses before I started working to photograph them. And I must say, to be honest, that third one, that was the last time I really enjoyed a total solar eclipse. It's just, it's a lot of work. So anyway, but I'd say you should definitely enjoy the experience of it. Now, the thing is, another aspect of photographing it is it's difficult in that your camera only has a limited range, a dynamic range, which means the difference between the light and dark that it can capture in a photograph. So depending on your settings, your exposure settings, it can, if it's a very short exposure, it can get this part very nicely, but it doesn't get the far corona very well. And if you change the exposure, well, the inner part now is very badly overexposed, but this outer part here is nicely exposed. And to get all that together, you have to do different exposures and then combine them, which is what I've done here to get kind of the full complete dynamic range of all that. But the wonderful thing is your eye is better than the camera at doing this. So the eclipse corona will look better than these here. In reality, it might depend somewhat on the sky transparency and so forth. But anyway, the experience is totally incomparable, though. But anyhow, the point is you can look forward to seeing even better than like this sort of photograph can show. Okay, so some other things, that's basically it. And then I should say also after the eclipse is finished, then it reverses. You go through the partial phases again until the sun becomes totally uncovered again. Okay, some other things you can enjoy. Well, the whole sky is really getting dark, actually. So planets that are around will show up as it gets dark, and bright stars also. This time, at least as a few weeks ago, there was talk of a comet also perhaps being visible in the sky too. We don't know a lot about comets. Those are another fascinating feature of our solar system, and they're very finicky. So we don't know if it'll be bright or not. But anyway, there are things you can look for. Temperature changes. Well, the sun is getting covered. And in fact, I was working on putting together, I guess it's here. I was working on putting together a plot from the 2017 eclipse. We had a friend actually who had a big thermometer, and she was measuring the temperature at different times. And so she started a little bit late during the partial phases, and the temperature was at about 66 degrees Fahrenheit at the start, and then it dropped 45, within an hour, it dropped during totality down to about 53 degrees, so quite a drop. And then she carried on longer after the eclipse ended. And a little over an hour later, the temperature was up to 75 degrees, so from 50 to 70. So it's really quite a temperature change. And so if you're interested in biology and the way nature and animals behave during these changes, you can observe that. Oh, shadow bands. Shadow bands, they're bizarre, but they're outrageously wicked cool things. They're just amazing, and it's actually hard to describe. But when the sun is very narrow, very thin crescent, thinner than this, the light comes through the Earth's atmosphere, of course. And probably what's doing this is the light coming through the Earth's atmosphere, which is shimmering and shaking because the atmosphere has a lot of motions and turbulent, rotations of the air and all this stuff. Well, the light's coming through that, and it gets spin and refracted and turned around. And the result is you get this pattern of shadows that are very subtle and hard to see, but they can show up and move around very rapidly in the ground. And the best way to see this is to set up just a white table or a white sheet on the ground, or just even a sidewalk, and look at that sidewalk. Now, shadow bands I had known about, of course, since I knew about eclipses. And then I saw, a couple of eclipses, the first two, and I always forgot to look for the shadow bands, because this is only a few minutes before totality, and the excitement is just hard to describe, and so you forget things. Then afterwards, you're kind of in awe too. So anyway, for the third one, yes, I set my watch to alarm, and I set it for 2 times. I set it for about 2 minutes before totality, and I set it for about 1 minute before totality. And that was just to remind myself to look for the shadow bands, and I had a place to look. So 2 minutes or so, my watch goes off, and I look away from the sun. I look on the white pavement that I had set aside for that purpose, and I saw absolutely nothing at all. So I went back and looked at the progress of the eclipse again, totally forgot all about this. And, some 55 seconds later or something, my watch goes off again. And I say, oh yeah, shadow bands. I look around, and this sidewalk is just loaded with them. They're just all over, shimmering all over the place. It is just amazing.
Dr. Sterling,
yes.
but you're out of presentation mode. Maybe if that was by accident.
Okay, there we go. Fine. Thank you. I was lost in the shadow bands. That's what happened. So anyway, that can happen. And so that's another strategy if you want to try and see them. And they're also they have a they're capricious too. They have a mind of their own. Sometimes they're there, sometimes they're not. We aren't really sure why. It might be the atmospheric conditions or what. So if you're in the totality, you might set your watch and look and see if you see them and make notes of the whether you see them, and if you do or if you don't, at the times you checked before relative to totality and your location and what the sky conditions are like. And if you send me what you find out, that would be very interesting, actually. Maybe you compile them and see who sees them and who doesn't. Okay, so, all right. So that's that. Let's see. Since this is the Physics Society, I thought I would touch a little bit on eclipse science. Would you like me to go for what, another 10 minutes or so, or what's the schedule here?
Yeah, another 10 minutes would be good.
Okay. All right, so I'll just skim through some of this. But so I might as well start off with the big one. This is the most famous solar eclipse experiment. And it doesn't have to do with the sun, really. But Albert Einstein, as you good number of you know, some of you just starting out may not be aware yet, but he did his theories of relativity. So in 1905, he did the special theory of relativity, which is kind of a special circumstance. And then in 2015, I think it was, he did his, or 19, I don't know what I said, being 1905 and then 1915, he did his general theory of relativity. And so those of you that don't know, this is really a wacko theory. I mean, but anyway, it says that space and time, I should say space-time actually, is curved, with more massive objects curving space more than less massive objects. So light travels through space and it sees this it follows curved space-time. So this effect really is subtle, though. I mean, you need something that is really heavy in order to see this effect. Just if you have a basketball or something, it's not going to have enough mass to see, to bend the path of starlight or something. So you need something big. So the sun is such a thing. And this is such a crazy sounding theory that the light path can be, and it's not only that, there are other crazy things too, can be warped by space and time. This certainly needed proof to establish it. Well, actually, the sun is heavy enough to do it. And so you can watch the light from stars near the sun, and that should affect it. So this is trying to picture this. The lines represent space-time, and this is the sun, and the sun makes this big dip in it. The Earth makes just a little dip in it. So it's hard to see the effect with something like starlight. But with the sun, there's hope that can be done. But the thing is, the sun, if you haven't noticed, is very bright. So you have to cover it up. Eclipse! So in 2019, Sir Eddington, or I think it was, actually did this experiment. They looked at stars, and very well, it's very well known, like how far stars are from each other in the sky. We can measure these distances quite accurately. So during the eclipse, if you see these same stars, are they equally far apart, or are they stretched out? So this is a picture of the asterism called the Pleiades, or the Seven Sisters. Sometimes these stars here. It's a beautiful sight if you have the chance to look at it in binoculars. But here's a picture of it, and then I just distorted it. So kind of this idea, if you put it near the sun, is it distorted? Well, Sir Arthur Eddington did try this idea in what is now Sao Tome and Principe, off the coast of West Africa. And it was found that the stars near the sun were displaced by the predicted amount, and that really established the validity of this theory. And this really, from what I read, is what really drove Einstein to be an instant celebrity. And that's why we know him so well today. I mean, it was in the headlines and the newspapers and things. So anyway, now we use it for a little bit more mundane things, but we learn about the outer atmosphere of the sun. And just quickly, the sun has 3 atmospheres. The bright part is called the photosphere. This very narrow part is called the chromosphere, and then the corona we've been talking about. The photosphere can have the sunspots in it, and then the interior, I'm not talking about today, but that's very exciting too. But the interiors, where the energy is made by nuclear processes, and the energy comes out to the surface. And the temperature, if you plot it as a function of distance from the sun, it starts off at like 50 or 60 million degrees K in the center, and it goes down to about 6,000 degrees at the surface. And then, but then it gets very hot in the corona. And actually, people didn't know this. They thought that the corona would be very cool because, as I said, the temperature is falling down to about 6,000 degrees, and people knew this back in the late 1800s. So they thought the corona would also be even colder than this. So they developed these spectroscopes around the late 1800s, and they took them off to eclipses, and they observed the corona, and they saw spectral lines. I'm not going into this. Some of you know about this. Others of you will learn about this if you're studying physics. But the point is, they saw spectral lines that they recognized, but they saw some they did not recognize, like this one, this green one here. And they just couldn't sort this one out. And they said, well, and these spectral lines are like signatures of elements. So they thought that there was a new element, which they were calling coronium. Well, other of our friends now, the predecessors, ancestors of some of our other friends, were saying that this didn't work. Those friends of ours, the chemists were making this table, the periodic table, about this time too. And they were saying, hey, sorry, you astronomy and physics geeks, you're saying all this stuff over here, but if you have an element like that, it's going to be over here, have to be over here to the left of helium, and it won't fit on our table. So you guys have a problem. And so, of course, the good guys, the astronomers are saying, no, you must have the problem. Well, turns out that this time the chemists were the right folks, and the astronomers and all were wrong. And it was found out So this was an eclipse in 1869 or something, when this was found, this crazy line. And about 1940, it was found out that these lines were caused by elements they knew, but they were just so hot that no one thought to look for spectral signatures of such hot things. It turns out the corona is about 1,000,000 degrees. So the temperature of the sun jumps up when you get to the corona. Why it does it? Well, we know generally how it does, but in detail, we still do to this day do not know. So this is just a couple of lessons here. So it was like 70 years from the 1870s or so until 1940 that this was a huge mystery of what these lines were, and different people with different ideas. And then it was found out that the corona is really hot. And we've known this from about this time. And all of my career, and even before it, people have been fighting with, well, what exactly makes the corona hot? And we're still doing it now. But anyway, we can see from satellites different aspects of the corona. I'll wrap up pretty soon here. But anyway, this is now from spacecraft. We can see the corona. It's very dynamic. The sun rotates about once a month. And so this is a very long-term image of it. And a lot of this is based on the magnetic field. A lot of this structure here is reflected by magnetic fields in the sun. So even in eclipse images, you can see the effects of these magnets. So it's like this magnet here, but you put it here, and there's a big magnet with this opening up here, and then more closed things on the sides, and then little loops here from little smaller magnets. So anyway, there's lots of eclipse studies, lots of solar studies going on, and there are eclipse experiments I could talk about if we want, that people are looking at. But I can summarize by saying that solar eclipses offer a special opportunity to undertake specialized studies, but for a limited period of time and location. And as I said, it helped establish Einstein's general theory of relativity. And it also led to the realization that the corona of the sun is much hotter than the sun's surface. Coronal and other solar studies are continuing with nearly every solar eclipse. Then there are also other studies, which I was on the slide, I guess, but I didn't talk about, like the Earth's ionosphere, and then animal behavior people are interested in studying. So that's going to close the main one, but I do want to show in the background here some of the dynamic excitement that we have on the of our studies of the sun. This is showing an eruption coming off the sun, throwing what we call a filament out and making what we call a solar flare. You can see the puny size of the Earth here by comparison. Here's another eruption here. You can see these things taking off, and they make flares, and so lots of stuff we study with these. And these are from satellites that we have in various parts of the heliosphere. Here's a nice one taken off here too. You see that flare brightening there. And then when these things get far away, they send out these huge things. Now, this is from a telescope out in space that actually makes an artificial eclipse. The circle here shows where the sun's bright surface would be. And this is how much you have to cover up here so that you don't get scatter lighting you can see far away, at least with this type of telescope. So eclipses can do much better because the moon can be really close. But anyway, these are very dynamic. These are called coronal mass ejections that shoot off, or CMEs. So a lot of us are studying these things too. So I'll close it out the presentation there. Thank you very much.
Thank you, Alphonse. We'll move to questions for your section, and then I'll briefly go over some of the other science projects. There was a question, what causes the solar flares?
Ah. How long do I have?
10 seconds.
Yeah, right. Well, I've been working on it for I don't know how many decades to answer your question. Basically, though, the answer is the same sort of story, though. It's the magnetism of the sun. We know that the energy that flares have, we look at the energy sources available, and we know it's only the magnetic energy. So really, these things here, like these things I'm showing taking off here, these are imbalanced in the sun for days or weeks, actually, just kind of sitting there. So then the magnetic fields are all in balance. But then something happens and instability comes about. The magnetic field is evolving on the sun because new magnetic field is coming up, and then it's interacting with field there, and so some of that magnetic field gets eaten away. And so the magnetic field basically that's holding this down gets interrupted. And so then it's out of balance, and the magnetic forces, rather than being in balance, the force trying to push this away becomes more dominates over that holding it down. And then it goes away rapidly. And then the rearrangement of those magnetic fields releases a lot of energy, and that's why you get this brightening here. So in a nutshell, that's it. The details we're still trying to sort out, though. Okay.
Thanks, Alphonse. You can stop sharing your screen, and I'm going to start sharing my screen.
Okay. Were there other questions, or are we good?
Yeah, we can answer some more after this portion.
Oh, okay, all right.
If you have more questions, put them inside of the Q&A box. I think some of them are being answered as we go along here.
Okay, all right, very good.
So I'm just going to highlight some of the opportunities for citizens, you all, or anyone to be involved in some of the science. Like Alphonse said, there are many opportunities to get involved. It's best to just observe. That's perfectly fine, and enjoy yourself and enjoy the eclipse. And let me see. But if you want to do something and contribute to some of the science, then there are a couple opportunities to do that as well. And okay, so I'm Samaiyah Farid again, and I am at NSF and I'm just going to talk about a couple of these science opportunities quickly. So all of these opportunities that I'm going to talk about, you can find more information if you go to this website here, the whole heliosphere and planetary interactions webpage hosted by NCAR. You can they list all of the opportunities that I show here in more detail. So the first one is the Light Sound Project, and what that is a way. It was originally designed to help visually impaired and non-sighted people enjoy the eclipse. And what it is a machine that transforms the light into an audible sound. And I just want to play a little sample of that, and you can hear it. So as the eclipse proceeds, then the sound type changes and frequency changes depending on what's being observed. So that's a cool little thing, and all you have to do is download the app, and then also request this tool from the organizers, and you can do that using the webpage link there. The other one is the Sun Sketcher, which also all you need is an app. And what you'll do here is observe the eclipse, and then during the time that a first and third contact, you'll be able to serve Bailey beads, as Alphonse discussed, which are these small, these bright regions here that you can see here when the moon's surface is just covering up the very last narrow brightest edge of this brightest edge is covering up there, and so the light shines through, and you can these are called Bailey beads, and you can record this using the app, and this will help many scientists understand better the photosphere of the sun and how it changes and how those motions relate to heating and evolution of the photosphere. So there's also the Globe Eclipse project, which is similar. Again, you just need to download the app, and the app will download several other sub apps. And during the eclipse, you can use the clouds tool to note the atmospheric conditions and how they change before, after, and during the eclipse. Also, determine the land features and things like how animals and plants respond to this changing amount of light and temperature, and also records the temperature change. As Alphonse says, it's often a huge drop in temperature during totality compared to the other parts of the eclipse. So all that information is very useful for scientists to understand how the atmosphere responds to the eclipse, and be useful for future work to be able to understand if we can predict where it really will be cloud free during eclipse times. So there's other apps similar to this, Eclipse Soundscapes. And again, that records insects and people and wind during the eclipse, and you submit your audio file to their project, and you can have it submitted as part of a larger database. So there are some other analysis projects. This one is one that I'm part of, that it's not too late to be part of the data analysis after the eclipse, where you will try to understand and map out features that we see during the eclipse, such as solar coronal jets and other transient features. And the Dynamic Eclipse Broadcast Initiative, DEB, is similar to that. You can also help with analysis after the eclipse is done of the data that they take here, but right now they're accepting existing teams only. And no matter what, observe safely. So those are all that I had there. And now we can go back to any other questions that you guys had in the chat.
I did see one here. Someone, I think, asked about eclipses on other planets or something.
Take that one.
Yes. Yeah. Okay. So, yeah. First of all, besides doing the sun, I'm also an amateur astronomer, and where I look at things and try and photograph things besides the sun, because that's my day job. But one thing you can do if you have a telescope, even a moderately sized telescope, but certainly not a big professional one's needed, you can look at Jupiter. Jupiter has all these moons, but it has 4 really big ones that were seen even by Galileo in 1609. And these moons, the planet is big, and then it has its moons that get actually quite far from it. But these moons actually go around Jupiter very rapidly. Over a few hours, you can actually see some of them moving. So there are times when the shadows of these moons actually fall onto the surface of Jupiter, onto the cloud surface of Jupiter. And you can see these, if you have a moderately sized telescope, you can actually see as a black dot the shadow of the moon going across Jupiter. So if you're on Jupiter, that spot, you would see the eclipsed sun by that. Also, the moons will go into Jupiter's shadow, and that would be like a lunar eclipse. There have been times that we've tried to see the effects of eclipses. Well, I think I'm going to leave it there for the moment. But yeah, people have thought about what eclipses can look like on other planets. Some of the measurements we've thought of trying are extremely subtle. Like we were actually trying to see some of the effects of some of these eclipses on some planets by looking at the intensity of the planets using Hubble data, but it was just too subtle and lost in the noise. But yeah, so people have thought about that. So I think we're ready to go on to another one.
See if we see any more questions. If we have more questions, put them in the Q&A. And a reminder that all of these, this presentation is being recorded and will be available. So all the information about options to be involved in Alphonses' talk will be available after this presentation.
So I wonder if anyone there is in the path of totality for this one. Would be nice. So if you are, then certainly I recommend that you do your best to observe it, doing it safely, and get involved if you like.
Also, Jessica has noted in the chat that if you're interested in ordering some free Eclipse classes, you can order them at the link that she's posted there, nsbp.org/eclipse classes. You can also reach out to me at sfarid@ucar.edu to request classes, and I will put you in contact with the people who can send those out. Okay, if there are no more questions, I can turn it back over to you, Greg.
All right, thanks, Samaiyah, and thank you, Dr. Farid and Dr. Sterling, for those good and informative talks. Hope everybody, like we said, take some time to, if you can, get out and observe the eclipse, whether it's partial or total, and to do it safely. And as always, stay safe. And if you're able to share the presentation on YouTube, share it out and share what you learned. All right, thanks everybody. This will be the end of our seminar.
Okay, thank you.